Welcome class to our lesson on AC machines. This is part of a larger course on electrical trade theory in Zimbabwe. AC machines, they can either be motors or generators. Motors convert electrical power into mechanical motion, while generators do the opposite, that is to convert mechanical motion into electrical power. So we have two basic types of AC machines. We have synchronous machines. On synchronous machines, the rotor rotates at the same speed as the rotating magnetic flask, which is made by the stator. Whereas in asynchronous machines, the rotor rotates at a smaller speed compared to the rotating magnetic flask. So we have a formula here, which is N equals to 60F over P, where N stands for the synchronous speed or the normal speed, and F stands for the frequency, and P stands for the number of poles. So you see us later on as we move on to calculations using that formula. But in this lesson, we're going to zoom into induction motors. So our next segment is induction motors. In particular, we're going to start by looking at three-phase induction motors. So three-phase induction motors, they have a stator, which is made up of three coils, either wired as a star or a delta. So we supply a three-phase current to a three-phase induction motor. Then the stator is responsible for producing the rotating magnetic flask. Now that rotating magnetic flask is going to cut the wires of the rotor, inducing a current in the rotor. That induced current in the rotor is going to produce a secondary magnetic field. Now, because of interaction between the primary magnetic field produced by the stator and the secondary magnetic field produced by the rotor, there's going to be motion. So the induction motors, they rely on the principle of electromagnetic induction. Okay, so more on that later on. So three-phase motors are the most commonly used motors. These are the advantages. The biggest one is that they are self-starting. A simple construction, efficient, available in many sizes, high operating torque, relatively cheap, relatively small in size. Then the disadvantages, three-phase supplies are not always readily available, like they're not available in domestic areas. Then they have complicated speed control. Then they have low starting torque. Okay, so let's move over to construction of a three-phase induction motor. So on a three-phase induction motor, we have a cooling fan to cool down the motor. We have a terminal box where we make the electrical connections. Then we have a stator frame, which is responsible for providing protection to the stator and the rotor. Then we have a bearing, which is responsible for reducing friction between the rotating parts and the stationary parts. So let's discuss the stator a bit. The stator is made up of the stator frame. The stator frame is just the metal casing, which is responsible for protecting the rotor and the stator. Then we have the stator core, which that is where we put our stator windings. Then the stator windings produce the primary rotating magnetic flask. Okay. Then with the rotor. So the rotor is the rotating part of the motor. So the rotor can either be a squirrel cage or a wound rotor. So a squirrel cage rotor have slightly skewed slots cut into their circumference. Okay, then advantages of squirrel cage rotors: have a simple, strong construction, require no maintenance, produce a smooth, silent operation, have a long lifespan. Okay, then we move on to wound rotors. Wound rotors are also called slip ring rotors or phase wound rotors. As with squirrel cage rotors, slots are cut into the circumference of the rotor. Advantages of wound rotors: a high starting torque, high starting currents can be limited, speed control is simplified. Okay, so we've come to the end of three-phase induction motors. Let's move on to single-phase induction motors. So single-phase induction motors are not self-starting because the single-phase supply does not produce a rotating magnetic flask. So in order to get a rotating magnetic flask, we need to split the phase of the supply current. So splitting the phase of the supply current is done using various methods, which are the different types of single phase motors. So the first type of single phase motor that we have a resistance start induction run motors. It is a lower torque. Then we have a capacitor start induction run motors with a high torque. Then we have a capacitor start capacitor run motors with the highest torque. So let's start by looking at the resistance start induction run motors. So you can see from the diagram that this is the main winding, which is made up of a thicker, smaller wire, isn't it? Which has a lower resistance and a high inductance. Then we have the rotor here. Then we also have the auxiliary winding. So on the auxiliary winding, it's made of a thinner, longer wire with a high resistance and a smaller inductance. This is going to split the phase of the supply current between the main winding and the auxiliary winding. So that phase shift is the one which is responsible for providing the starting torque required by the resistance start induction run motors. Okay, so I'll repeat because we're splitting the phase of the current between the main winding and the auxiliary winding. That is what is going to provide us with the starting torque for the resistance start induction run motors. Then from a resistance start induction run motors, we move on to the capacitor start induction run motors. So the diagram for the capacitor start induction run motor is similar to the resistance start induction run motor. We have a main winding and we also have an auxiliary winding. Then the auxiliary winding is connected in series with the capacitor. So a capacitor in general, it is a leading power factor, isn't it? So the phase difference between the current in the main winding and the current in the auxiliary winding is going to be much larger compared to the phase difference in resistance start induction run motors. So this capacitor start induction run motor, it has a higher torque. Okay. Then from there, we move over to capacitor start, capacitor run motors. So on a capacitor start, capacitor run motors with the main winding, with the auxiliary winding. And the auxiliary winding is then connected in parallel to a start capacitor, which is also connected in series with a centrifugal switch. Then we also have another capacitor, which is the run capacitor, which is connected in parallel with everything else. So this type of motor is a much higher torque compared to the other two. As usual, guys, like, share, and subscribe. To get more information, I encourage you to download the books in the description below.